Hi guys, welcome back. I've spent ages here using a new model which I downloaded, running on my machine locally. It's not running online. In fact, there's no internet being used in this demo, and it's the Ministral-3 one. Um, and I'm using the Ministral-3 latest. It only came out, I don't know, I think it was about a month ago or something like that. The good thing about it is it's a vision model. It's very good at text as well. Some of the vision ones just kind of do vision, but this one can do maths and vision, so it's particularly clever. And I'm going to show you some demos of it working, doing maths from a camera. So it's going to take pictures of problems as well as other things. And I'm also going to show you a new plotting routine which I have managed to get working, which plots latex directly. So before I do that though, I'm just going to show you this is the program, and let's get it running. I'm not going to put the reverb on for the main program because I know it annoys some people. I'll just put it on briefly just for special effects for the initial demo, for the initial part, and then for the maths I'll take it off, and I'll take off the, here I've got a new lovely avatar which is a sphere. Looks a bit like a jellyfish sometimes when it moves. Let's start it up. Anybody there?
Hello. How can I assist you today? Do you have a question, a mathematical problem, or perhaps an image you'd like me to analyze? Let me know.
What is today's date?
Today's date is Wednesday, December 31st, 2025. Happy New Year. Party Popper, would you like anything related to this date, or can I assist with something else?
No, let's just get on with the demos. What do you see?
I can see a handwritten differential equation on a piece of lined paper. The equation is written as dv over dt plus 2v equals 1 with the initial condition v0 equals 0.
Solve the equation.
To solve the first order linear differential equation, dv over dt plus 2v equals 1, v0 equals 0, we use the integrating factor method. Here are the steps. 1. Identify the standard form. The equation is already in the form dv over dt plus ptv equals qt, where pt equals 2 and qt equals 1.
Okay, stop. Graph that.
Plotting the function.
What do you see?
I can see a handwritten problem asking to find a characteristic polynomial of the matrix bracket matrix containing a equals 1 0 0 2 2 0 3 4 3.
Find the characteristic polynomial.
The characteristic polynomial is boxed minus lambda cubed plus 6 lambda squared minus 11 lambda plus 6.
Graph that.
Plotting the function.
I'll just check this. Oh. That's at 3. That's 0. And then I'll make y max 1, that minus 1. Just scaling the polynomial. I can see the roots are 1, 2, and 3, which is correct. I can, of course, reverse that and make that first coefficient positive, and it'll flip over. Multiply the polynomial times minus 1.
Multiplying the polynomial by minus 1 gives boxed lambda cubed minus 6 lambda squared plus 11 lambda minus 6.
Graph that.
Plotting the function.
We've got the same thing upside down here. If we look at it, we've got 1. I've already got 1 there. Minus 1. And my max will make 1. Don't think it matters really. Oops. If I don't, oh yeah, you see. This needs to go to, oh, of course, needs to go to 3. I'll make it 4 actually. There we go. So there are here's the first one. The roots 1 to 3, actually just make that 4 as well. So that's the original one. Here's the flipped one, which is kind of obvious. It's exactly the same, just flipped over. So let's try some other examples. Integrate x log x.
The integral of x natural log x is boxed squared over 2 natural log x minus x squared over 4 plus c.
Graph that.
Plotting the function.
It only takes time here because I've got to squeeze it down so you can see it in my captured area on the screen. There it is. And there's the graph. So that's how we can solve basic mathematical problems. Let's do another one. I can type it in this time perhaps. Differentiate x over x plus 1 squared. So it's differentiating x over x plus 1 squared. It's given the answer. Graph that.
Plotting the function.
There it is.
Plotting the function.
It heard me. So there it is in 2 halves. 1 minus x over x plus 1 squared. Show a 5th order polynomial. Oops, let's do it. Show a 5th order polynomial.
Here is an example of a 5th order polynomial, a quintic polynomial with arbitrary coefficients.
Stop. Graph that.
Plotting the function.
There it is. I'm not going to do it in words this time. I'm going to say find, let's say, show the first 6 terms of the Fourier, let's see, no, the first 6 sine terms of the Fourier series of our square wave, amplitude 3, and duration, that's the period, 1 second. And shortly it should get the Fourier series.
The Fourier series for a square wave with amplitude 3 and duration 1 second fundamental period t equals 1 is given by foot equals 4a over pi sum from n equals 1, 3, 5 dots to infinity of 1.
Display
I'm here to help. Let's make sure you get what you need, whether it's the correct Fourier series terms.
Display the solution on its own.
Boxed feet approximately 12 over pi sum over k equals 1, 3, 5.
Show the sine waves on their own.
Here are the individual sine terms of the Fourier series.
Add them up and show the final equation.
The sum of the first 6 sine terms for the Fourier series of the square wave is boxed feet equals 12 over pi sine 2 pi t plus 1 over 3 sine 6 pi t plus 1.
Graph that.
Plotting the function.
At last. I'll just make sure this is, make this 2, just make it 0. Scale it down a bit so you can see it. And there's the first 6 terms. Took a little bit of a while to get it. So unless you get it in the right form, of course it's not going to plot it. So it had an approximation symbol there to begin with, so it wouldn't be able to plot that. But it's got the first 6 terms, and there it can plot it. It's got the amplitude 3, and the duration should be 1 second. Yeah, so it's going from 0 to 1, or 1 to 2 is the period. And that's the Fourier series. I can save that and read it in. Can also go in reverse. I wonder if this will work. If I read it in, I need to get the image on. There's the images. Let's load one that I had earlier. Here's one of amplitude 1. It's got very tiny writing on it. Let's see if we can read that. Describe the image.
I can see, the image shows a plot of a trigonometric function defined by the expression y equals 4 over n sine 2 pi x plus sine 6 pi x over 3 plus sine 10 pi x over 5 plus sine 14 pi x over 7.
Show the equation on its own.
Here is the equation shown in the image in its own boxed form.
Graph that.
Plotting the function.
You can see it's recreated the waveform. That's the original image, and it's recreated. Now of course I can scale that to make that 1. I'll make it -1. So we all know from school, with sine terms, you I say school inverted commas, you have to have odd functions. So that's why it's come out. Otherwise it would be cosine terms. It would go across the negative, be a symmetric function. So we've got this. It's recreated the same image from the picture. So taking a picture of the picture, and then loaded it in and say, can you read what's on it? And it's read the formula of what it is, and then it's recreated it. I picked it so it's at a different amplitude from the other one, so you know what, it wasn't cheating, because the previous one had an amplitude of 3, so it's the same duration. Thanks. Well, I'm going to do a harder question now. I'm going to do an RLC circuit, which is a second order differential equation. Now I could approach this from Laplace transforms, but I'm going to do the traditional differential equation thing. It turns out that when I use the camera in real time and the screen recorder to record this, it crashes the whole system. I think it's a memory problem, obviously. So I'm just going to use a photograph I've already taken of a piece of paper which I've written a second order differential equation on. Now it's an underdamped system, so it should have a bit of overshoot. And I'm just going to load it in and then get it to analyze it, solve the equation, and then I'm going to plot it. And that'll be the demo over with. So let's get going. So if I start this, I can then load the image. Describe what's in the image.
I can see, the image shows a handwritten mathematical problem involving a second-order linear differential equation. The equation is written as d squared v over dt squared plus dv over dt plus 0.5.
For 0 initial conditions, solve the problem.
To solve the second-order linear differential equation with 0 initial conditions, d squared v over dt squared plus dv over dt plus 0.5 v equals 1, v0 equals 0, dv over dt sub t equals 0. We proceed step by step. Step
Okay,
1.
stop.
Write the homogeneous
Stop.
equation.
Graph that. Graph that.
Plotting the function.
Can you check the solution? I think there's a mistake.
You're right to double check. Let's carefully verify the solution step by step. The issue likely lies in the derivative calculation for the initial condition dv over dt sub t equals 0 equals 0. Revisiting step 5, derivative calculation. The general solution.
Stop. Show the final
I didn't catch that. Could you please rephrase your question?
Show the final equation.
Here is the final corrected equation for Vt. Boxed Vt equals 2 minus 2e to the power of minus t divided by 2 cosine t over 2 plus sine t over 2.
Okay, graph that.
Plotting the function.
So I'm just going to reduce this in size a little bit so you can see it. And I'll scale it to 15 seconds that way. And well, it's kind of right anyway. Just put y minimum to 0. Put y max to 3. And there's the step response, and there's the equation, which I'm just checking it at the moment. 2 minus 2e to the minus 2 t sine x over t. Yeah, that looks correct. Yes, that's the right solution. Now you see it's underdamped. It's got a steady state value of 2, which makes sense from the equation here. When t goes to infinity, that goes to 2, and it also makes sense from here. The this is the characteristic equation. It's like s squared plus s plus 0.5, when s goes to this, when these derivatives are 0, it's steady state, and you get 1 equals 0.5 v, so v goes to 2. That's an old-fashioned way of working out the steady state from derivatives. It's the sort of thing that Leopoldov would have done or something in his day, but we would nowadays would put s to 0 in a Laplace transform. But there you go, there's the solution. We can do a number of things. I just wanted to show you the MATLAB solution, just to prove to you that it was in fact correct. So here's the MATLAB. I don't know if I can get it down to size. So here's the MATLAB solution. I basically worked out the transfer function and then put a step up it, and that's well, I'll just put the maximum to 2.5 and then we can compare them. They should be pretty much identical now. Oops. Hate it when Windows does that. It's quite tricky to scale these things. Oh, never mind. That's the that was the plot disappeared now. But that's the original one and the MATLAB one I just showed you, and they are the same because I checked it thoroughly before I did this. So that's quite interesting in that it's another way to solve problems other than MATLAB, a much quicker way if we can rely on AI, of course. As you could see, it does make mistakes, so you've got to watch it. The reason I knew it was a mistake the first time, apart from the fact that I checked it before, of course, was it because it had an undershoot on it in the first time it did it. And I know that that's only nominum phase systems that are undershoots under specific conditions, so there's no way you could get that. But there is a way you can get it with an initial condition. If the first derivative has got an initial condition, you can get it as well, which I didn't even know myself after all these years. But you can get that as well. So it made a mistake with that as well. But when you get it to check its results and correct it, you can see that it ends up with the right values.